As we start to look more into depth on AC circuits, we're going to introduce this whole idea of impedance. And really, impedance is nothing more than the more general form of reactance and resistance. Both of them play some similar roles, but there's pretty different. So from before, or we can guess that from Ohm's law, the Vrms is equal to Irms times this new quantity impedance. And we see that for resistors, this value is an R. For inductors and capacitance, this value turns into an X. So we may guess that for AC circuits, this is going to be a very similar role to what we've seen with resistance, capacitance, and resistance and reactance. However, we're going to generalize it to see how they all actually work together. And the general expression for impedance for an AC circuit is as follows. The impedance is given by the square root of the resistance squared of the circuit plus the inductive reactance minus the capacitive reactance quantity squared. So we can see that they are related, but they're not just straight adding it together. We add it more like a Pythagorean theorem adding. So we'll see that Z is kind of a combination of the two, but the two definitely have a distinct properties. And we'll notice that this value right here, if we don't have an inductor nor a capacitor in here, that we get the square root of R squared. So we get our normal V equals IR up here for that case. And similar for the other ones, we can get the Vrms equals Irms times X if we have just one of these X's. And actually, even if we have a resistor or a capacitor and an inductor together, we can add the two together and we'll get just the normal addition of the two. So as we said before, X sub L and C sub L are the inductive and capacitance reactance of the circuits. And as we said, if both of those are 0, we just get out our original Ohm's law. However, we have these additional values of X sub L, and just as a reminder, X sub L is omega times L, the angular velocity times the inductance of the circuit, and X sub C is the capacitance, the capacitive reactance, which is equal to 1 over the angular frequency, omega, times the capacitance of the circuit. Now, if we want to add impedances together, if we have a simple series, we have all these components in series, then it's just adding the impedance of each of the individual parts. Similar to like resistance, we get to do this again with impedance. And if we have things in parallel, we get the familiar form like we had for resistors, that 1 over the total impedance is equal to 1 over the individual components if they're in parallel. So the impedance not only gives us how the circuit is going to obey in terms of Ohm's law or related Ohm's law, that the RMS, the voltage RMS is related to the current RMS, but we're also going to be able to get the phase angle out. And this is something we saw in the previous ones where we had 90-degree phase shift, either leading or lagging one of the two things. We'll see that the phase shift in the general form is given by the tangent of theta is equal to X sub L minus X sub C divided by R. So if there's this wonderful case where we have an equal reactance for the inductor as for the capacitor, that this phase shift will be 0. And we can get any of the values for this. And it works out pretty well, and we'll see that these phase shifts, the difference between the voltage and the current, will be governed by this phase shift.